Renewable energies come in many forms. One of the absolute most useful one is hydropower, actually using the potential energy that's stored by having water flow downhill. Small-scale hydro is defined by meaning smaller size dams, mostly where the water wheels themselves are external to the dam structure. You can't really say, oh, that's large and that's small. There's everything in between. But if you have a small stream going through your community, you might wonder, how much energy could we get from it? So let's talk about energy from hydroelectric power. What we really want to know is watts. Energy per unit time. How many hair dryers, how many light bulbs could you run? How many 100-watt light bulbs? How many 1,000-watt hair dryers? So we need to have a formula. Power, as you recall, is equal to energy per unit time. And energy comes from the potential energy of having this stuff fall through some height. And that potential energy is mgh, the mass times the height of which it's going to fall times gravity, because we live here on Earth. And we divide this by time. Now, the height is fairly straightforward. This is a quantity we call the head. So if I have my dam here, and water is so high up here, and it's so low here, this distance right here, this is going to be the height, h. There's a minimum for small-scale hydro. H has to be at least 2 meters. If you don't have at least 2 meters, it's probably not at all worthwhile doing this. Out in the boneyard, didn't exactly have 2 meters, but we still wanted to calculate how much energy we could get. What about these other things? G, gravity. Gravity on Earth, 9.8 meters per second squared. 10, close enough. All right, that's the gravitational constant. Now, all that's left is mass per unit time. How am I going to calculate mass per unit time? Well, one thing is you could just have a bucket and weigh it and see how long it takes to fill up. But it's much better if you could just measure the cross-section, the flow velocity of the stream. If I have a stream, let's imagine I took a cross-section of that stream. Right? So here's my stream, here's my units of water, large slab of water moving down the river. So this is a way you can actually measure it, right? Because there's going to be some depth of the water here. There is going to be some width of the stream. And if I put a float on here and watch that float fall downstream, I can get the speed of the stream. So I could get, say, the distance that it flows along, and I could time how long it takes for the float to move from here to here, and that would be my time. You say mass per unit time, and you've told me things about the volume of the stream. Well, that's right, because if I want to get this whole equation here, mass per unit time, I could take the volume of water, which is going to be the L times the W times the D. And of course, this is going to be over that T, this time, right, that it took my float to go here. D over T is the velocity, the speed of the stream. This is volume. I want to have some quantity that gives me mass per unit volume. This quantity is known as the density. And the density of water is 1,000 kilograms per cubic meter. So, I want to get back to my power. I've got these measured. I can measure the width of the stream, the depth of the stream, the speed of the stream. This is volume, this is volume, this is mass per unit time. I then take it by the height of the stream. It's call that H. I can then put in gravity, and I'm going to need one last thing, and that's the efficiency of the turbine. 100%, that's your number. But not every turbine is 100% efficiency. So I'll have one final quantity, the efficiency. All right, so how much power are we going to get? Remember, power is energy divided by time. You already knew that. Everyone can see that. Now, the height is pretty easy. I'm going to put in that dam, and we're going to see how high of a head, they call it head on a river. How much above the base level is the water? We're not going to get much here, but we are going to try to see that. First, I have to get the depth, the mighty height of this water. I'm trying to look for some average place. This looks pretty average. And we're going to measure it. Whoa, 5.5 inches. 4.5 inches. 5 inches. Now, inches are crazy American measurements. They're not even British, they don't even use them. So we have to convert that to meters. It'd be much easier. Centimeters. I'd say that's about 10, right? 10 centimeters. I like nice numbers. I can multiply them easily. All right, so that is L, 10 centimeters. Now here, help me out here. Okay. We got to measure the width of this mighty river. Okay, hang on. All right, this is 12 feet to here. That's all the longer my tape measure is. Hang on, you can let go. Okay. It's all right. Here, grab that. Oh. Okay, go right up to the edge of the stream. That water's not there. Where the water is. Okay, that's 8 feet. Looks like 20 feet. How many meters is 20 feet? 6. 6, right? Because meters more than a yard. We've got the depth of the stream, L. That was 0.10 meters, more or less. And we've got the width, and that was 6 meters. Why don't we go 5 meters? No. That's 15, 16, that's about here. Okay, about there. That's about 5 meters. Okay, you got your timer? Okay. Do I really have to use the second hand of my old-fashioned analog device? Looks like I do.
I gotta watch.
You gotta watch. Okay, can you get ready your time? Okay. Here, hold this. All right. So, we got a guy where this racing flow is. Okay, you ready? You ready? Go! Come on, you can do it! And when it reaches across from you, perpendicular, you yell stop. This is a fast-moving stream. Stop. All right.
18 seconds.
18 seconds. We have the distance was maybe 5 meters, and we have the time was 18 seconds. Okay, good. Where's that original? Right here. Yeah, okay, it's stuck on a weed. Don't worry, we're going to dam up the river. It takes a while to dam it up, and we don't know the height yet, so now we're going to dam up the river. I need a rock. be successful until the water starts coming over that cement spillway. So I really have figured out what my maximum height of this boneyard dam project would be. Now it's quite possible that you could make a much bigger dam and have a little lake back there, right? Instead of an island behind Engineering Hall. So you could, in principle, make higher head. What we're actually going to get is maybe probably about 8 inches, which would be 20 centimeters. So I think we could probably get from this exact project right here 20 centimeters, 0.2. Now we need to multiply. So we're going to have power. That's going to be power in watts. Time, distance over time, 5 divided by 18 times 6 times 0.1 times 1,000 times 10 times 0.2. All right, let's do a little math. 10 times 0.1 is 1. 0.2 times 5 is 1. 6 over 18 is a third. So, and a third of 1,333 watts. 3 light bulbs. But remember, there is one more important factor that's worth another 2 points on your test when I ask you this question. Can I really take all this 333 watts of raging energy and capture it at 100% efficiency? I doubt it. I doubt it. So, what is the technologies of small-scale hydropower? The key is to have a good water wheel. Now, I'm sure you've seen cases where there's a stream flowing down the hill in the mountains, and they give you really good water wheels. They probably look better than this. But this is what we're talking about. You need something for when not the wind blows, but the water blows through this giant stream here, that it turns it. Like that. Look at it turn. Of course, I've dammed up the river. Right.
Do it once you take the dam out.
Yeah, there we go. There we go. For small-scale hydro, there are 2 minimum requirements. First is you need enough head. 2 meters, 6 feet. If you can't get 6 feet, forget it. It really isn't going to work. There's enough room for the turbine. You don't use something that small after all. It's got to have some height on it, right? So that's an important thing. And the second is, if you do have one of those turbines, its efficiency is actually around 0.6. So there's one more thing in this equation, which is the efficiency of the turbine. So let's say we can get 6/10. All right? That now is 200 watts. 200 watts. 2 light bulbs. Way short of a hairdryer. What are some of the advantages and disadvantages of hydropower? Doesn't give me an advantage. What is it, Harsh?
Doesn't produce carbon dioxide.
Yeah, no carbon dioxide, right? It's that renewable energy system. You guys got the, okay, you got that up there. Someone's got to come out and get this power. All right. I got to finish it first. All right, what else?
As long as there's not a drought, you practically have it.
As long as there's not a drought, you've got a clean energy source. Remember, hydropower does about 2.8 quads of energy in the United States. We roughly use 100, so it's something around 2 to 3%. That number goes up and down every year. And we have not built any new dams. It goes up and down every year depending on how much it rains in the reservoirs. If it doesn't rain in the mountains, you don't get any hydropower. So, it's a wonderful, potentially free source of energy. What are some other advantages of hydropower? What about the nice lakes that you use? Well, you got nice lakes you can use, right? The stuff upstream of the dam provides a recreational area. Also, it can store your fresh water. You could go and use it for irrigation or drinking. You don't have to run it down the dam to get electricity. What are some of the disadvantages of hydropower? Yeah? You can't do it everywhere, right? You can only do it in a place where, well, you've got a river and a mountain, or a lot of elevation. That's why Champaign, Illinois is not the spot for hydropower. We don't have a lot of elevation variation, right? Okay, what else is a disadvantage? Navigation, right? Certainly if you're going up, or ecological disaster on the downside, right? All that flowing river is now stopped. There's also a very important one, which is, what about the communities that used to live in the mountain valley before you put the dam in place? And you made this reservoir, you made this giant lake. The largest dam in the world is the Three Gorges power plant in China. It makes 22,500 megawatts. That's equal to 22.5 giant coal power plants. It's wonderful. But they had to move more than 1 million people that used to live where now is a giant lake. So you certainly are flooding things upstream. And then of course you also have the potential of major disaster. Because after all, what happens when the dam breaks? All right? Throw it upstream. All right. We will certainly shortly find out what happens when the dam breaks. All right. Oh, wait. I think it needs a little human assist. Okay. Okay, ready for the wave?
Do you want us to dump the rest out? Out on his head.
Outside.
Look at that tidal wave! All right. Go ahead. Aim for my head. Oh, that's kind of cool. There was a reason I was playing Smoke on the Water. Can't you use it on the ocean? Well, we've talked about tidal power, which in a way is the same thing here. Remember how if you could have the high tide come in, you can hold it behind a barrier, and then you just make a small-scale hydro plant and let it all go out twice a day, right? Next high tide, you fill up the barrier again. There is another type of small stream power, just like you could use the water currents underground. If you have the water going down a hill, you just stick some water wheel in, right, and it turns it. And there's another way to get power from water, and it has to do with the waves. So I have a wave energy device, completely non-functional, but It's got the right pieces. I just have to make a wave. So I'll stick my dam back in. We'll make another wave here shortly. Right? So you anchor this someplace. Where did it look like we had a big wave? Like maybe here, right? All right. You anchor this. And you could imagine that if there were big waves, that buoy would be going up and down, right? So let me once again make a wave by damming this again. Keep your eye on the styrofoam. If you had a compressor or something that every time it stretched, right, it would produce energy, then it would contract and it would run it back the other way. That's how you can make it with waves. So here I'm going to try to make a wave, and of course you should see the styrofoam bob up and bob down. Every bobbing up and down motion could produce a little bit of charge to get stored in the battery. Wow, look at that wave power! Now the real uses for that are places where it's very hard to get electricity to, especially literally buoys marking rocks and other dangerous spots out in the ocean. So they have a battery, they charge up the capacitor at night lights up a light, right, which warns people, don't go near there, something's dangerous, right? So wave power has some niche type of markets. The United States has created all of the dams on the major rivers that we really have. So there's not much growth potential. But that's not true across the world.
I just spoke to a man who got back to Costa Rica and there's a huge hydropower push there.
Okay? And another country where there is a lot of potential is Turkey. Very mountainous country, lots of rivers that have not yet been dammed to produce hydropower electricity. You're not using the water up. It's not like, oh my God, that water used to feed our cities or irrigate our fields. Water's still there. You're just taking advantage of it falling down the mountain. So in those cases, it's almost an ideal renewable energy resource. Large scale always works on having a pressure difference. And embedded in the dam itself is a type of turbine that turns because the pressure's higher on one side than the other. Small scale hydropower works by having what you kind of imagine in the old movies or the westerns, the paddle wheel, right, where the water kind of shoots at it and comes through. Even in this type of small scale hydropower, we'd have a wheel and the water, which would be coming out from the bottom of the dam, would be kind of pushing against it, turning the wheel. Different types of systems that are embedded. In the big dams, like Hoover Dam, all that stuff is inside the massive concrete itself. You never see it. In the small scale, you almost always will see some wheel going around. Small scale, like this one, you get a few hundred watts. Obviously, medium-sized rivers, like in Dixon, Illinois, you can get a few thousand watts, maybe tens of thousands. You can add those up, but the spots that are still available across the country are fairly low to be able to do that. And land use, creating the uphill reservoir is always a potential problem because someone probably is already using that land for something, and now you're going to turn it into a lake. Right, so there's a question, is there a technology difference in obtaining it from fresh or salt water? There's a technology difference in the large scale versus small scale in terms of the efficiency. The turbines in Three Gorges Dam or in Hoover Dam are 85% efficient. The larger pressure difference, you can get a more efficient turbine. In terms of using salt versus fresh water, you just have to worry about gumming up the works. So all sorts of things live in salt water and more things grow. All right, smoke on the water. You heard it here. Have a great day, everyone. All right, so the raging torrent of the Boneyard Creek in Champaign-Urbana. gives you 200 watts, at least on this particular late March day. 200 watts, not going to be terribly worthwhile. Of course, that was not with the 2 meters of height. That was with 0.2 meters of height. So you do 2 meters, maybe you get 2,000 watts. Let's talk about turbines. What kind of turbine would you use? Well, here's a picture of one. This type of turbine is what is typically used in this type of stream where you actually have the water spitting at it. The diagram that you see here actually shows how the water could come out right here, pushing against those types of cups in the turbine blade. And this water will have a certain pressure because it has this drop of height. And that water pushes against those and the turbine spins. And those types of turbines, these small scale turbines, 0.4 to maybe 0.8 efficiency, I'd say something like this, maybe at the 0.6. And the 200 watts we calculated was assuming a 60% efficient turbine. If you don't have a lot of pressure, you don't get as high of efficiency. Of course, this type of turbine is also useful that you don't necessarily need to make a dam. You could just have the water coming down the hillside, and the pressure from the water itself could turn these, just like you see in many places where they use a water wheel to do some type of work. Advantages of small-scale hydro are if you've got a rolling stream flowing down a hill, stick in a turbine like this, get some free power. If you've got to make a dam, my guess is the number of kilowatts you're going to end up with is probably not going to be worth your construction cost and your turbine costs, and more importantly, what happens upstream of the dam. Chances are that land was being used for something else, like your neighbor's house. They might not appreciate it when you suddenly put them underwater. That's what you need to know about small-scale hydro.